All right, so I'm not going to waste hour times working out a numerical example from the homework, but I can definitely kind of show you what you should be doing. So let me pull it up really quickly.
Bad idea.
Um,
Not necessarily a bad idea, it's just wasted.
kind of. I'll explain, like generally speaking, it's a good idea, but for these particular problems, I would think that it's a waste of time. Open up. Open, stop trying to rename the damn folder.
Give it a check.
Your mom has a check. All right, so let's just look at this one really quickly. So let's go to draw. So this part right here that I've circled in purple, what is that? That's the amplifier part. It is, the input signal is applied to the source, the output signal is taken at the drain, so this is a common gate amplifier. Okay. Then we have this part down here. What is that? Well, that is a diode connected NMOS transistor, which means it's going to look like R naught in parallel with 1 over GM, right? This is playing the role of the emitter resistance. So whenever you have a common gate amplifier, you literally just replace RE with this guy right here and use the relationships that we developed last quarter. It doesn't have to be harder than that because that's literally all you need to do. If we go to this guy right here, this is the amplifier portion because I have an input signal and an output signal on the same transistor. We're not going to have that luxury for much longer, but we'll get to that. So this is a common source amplifier. This is a PMOS device that is diode connected, so it's going to look like R naught in parallel with 1 over GM, and this is taking the role of our drain resistance. This guy right here is also another diode connected transistor, so it's going to look like R naught in parallel with 1 over GM, and it's taking the role of the emitter resistance. I don't know how and or why that got moved down, but we won't worry about that. This guy right here is the amplifier. So what type of amplifier is this? It's a PMOS. That's important here. Okay. So the drain is on the bottom, the source is on the top for the PMOS. So this is a common drain amplifier. And then this bit up here is actually can be potentially difficult. I think it's taking it. So this guy right here is a PMOS current source, effectively, right? So it's going to look like just R naught P. But it's effectively being degenerated by another one. So realistically, what you should do in this case, or at least the easiest way to do it until we learn about cascodes in a couple of days, because this is actually an example of a cascoded current source. Is draw the small signal model of everything above the red line, where you're treating this guy, this topmost transistor, as R naught, and then do the full small signal model for this middle one, and you'll be able to figure out what the impedance of that network looks like as a whole. So number 3 is the only one that should be remotely actually difficult. The other two should be really, really straightforward. Okay. All right. So now I have 11 pages of notes on current mirrors. So first thing I want to do is kind of set up why current mirrors are going to wind up being so important. They are like a fundamental building block of both digital integrated circuits and analog integrated circuits. We will see them everywhere. And actually, you've already seen them if you were paying attention to the transistor amplifier that I showed you guys way back in circuits 2, like the large model of the 741 op amp is literally lousy with current mirrors all over the place. It has some normal ones, a couple of specialized ones that we're going to learn about in Monday's class meeting, all of that kind of good stuff. So very, very fundamental to the operation of integrated circuits. So I want to talk briefly about why they're so important. So we're going to start by looking at a simple BJT resistive biasing stage, right? So let's say that I have my supply voltage VCC, some resistance here R1, some resistance here R2. This is going to be transistor Q1, so I'm going to use Q for all of my BJTs, M for all of my MOSFETs. And we don't really particularly care what's connected to the collector terminal of this transistor Q1, which is why I'm just putting a ... here. It might be more transistors, it could be a resistor, it could be a direct path to ground, it could be a direct path to VCC. We don't know, nor do we actually care at this particular moment in time, right? So this is our collector current, IC. Here's our base emitter voltage, VBE, and we should be able to see that our base emitter voltage, VBE, will be approximately equal to VCC times R2 over R1 plus R2. That's literally just our voltage divider relationship. And the reason why I'm saying approximately is we know it's not going to be quite that because we're going to have some base current that's going to cause that voltage to vary very slightly from what that value is. We are going to neglect that base current here just to have a more simplistic understanding of what I'm trying to illustrate to you guys. This base emitter voltage is related to the collector current, assuming that we don't have any early effect to worry about, by the relationship VT times the natural log of IC over IS, right? So the problem with this representation or this resistor biasing scheme is that it is very susceptible to variations in both the supply voltage as well as the operating temperature, right? So let me explain what I mean by that. So number one, Any fluctuations in VCC cause a variation in VBE, and thus also IC, showing that the DC operating point is strongly dependent on VCC, meaning that if we don't have a stable power supply, then our operating point is going to change significantly. And if this biasing stage is used to bias, say, an amplifier, that means that our gain is going to vary widely depending on what our supply voltage is. Our input and output resistance are going to vary depending on what our supply voltage is. Generally speaking, it's just not a good thing for sensitive microelectronic devices, okay? So we have power supply dependence. We also have temperature dependence. So let's talk about this a little bit, okay? Now, one of the principal reasons that we use a voltage divider to bias things is because the voltage divider in and of itself is temperature independent. So the resistor values will change, but they'll both change by the exact same amount. And so the ratio of them will always be constant. So that's not where our temperature dependence is going to show up. Instead, we're going to see our temperature dependence mess with our thermal voltage VT as well as our saturation current IS. So those two quantities, VT and IS, are heavily dependent on temperature, right? The fluctuations in operating temperature cause changes in VT and IS, causing IC to change to keep VBE effectively constant, right? So now let's look at a MOSFET and see if it fares any better. So our MOSFET circuit would be something like this. Where I'm going to call this transistor M1. Here is our gate source voltage VGS. Here is our drain current ID. And assuming that our device is operating in the saturation mode, our drain current ID should be approximately 1/2 mu n Cox W over L times VGS minus VTHN quantity squared, where I'm neglecting channel length modulation effects just for simplicity's sake here, right? I'm now going to substitute in for VGS, and so this is going to look like 1/2 mu n Cox W over L times VDD times R2 over R1 plus R2 minus VTHN quantity squared. And we can very obviously see that our drain current and our gate source voltage are highly dependent on VDD, much like we saw previously. Where are our temperature dependencies going to show up in this. So our threshold voltage is dependent on temperature, and our carrier mobility is dependent on temperature. So we're going to see very similar effects, even though it's different quantities that are exhibiting these temperature dependencies, right? So having a high degree of dependence on supply voltage and temperature, for some circuits, it's really not going to matter. But for other circuits, it's going to be incredibly critical. So let me explain what I mean by that. Let's take your cell phone. How frustrated would you be if your cell phone didn't work? Pretty frustrated, okay? Now, let's think about something here really quick. What's the power supply for your cell phone? It's battery, right? So does the voltage that's provided by the battery of your cell phone remain constant? No, it changes with temperature. It changes with how long you use your device, which means all of the different amplifiers and all of that kind of good stuff that are inside of your cell phone, if they changed with just the state of charge of your battery, they would all be absolutely terrible amplifiers because they would all be constantly changing as you use that device. So for sensitive microelectronics, having some dependence on temperature and supply voltage makes it really untenable to be used for practically anything, okay? So in order to mitigate that, people much smarter than me have come up with different schemes that are based on effectively temperature invariant quantities, okay? So in order to generate supply and temperature independent voltages and currents for high performance microelectronics, people have devised circuits like the one that I'm about to draw. And by the way, this is a simple one and it's still real gross, which is called a band gap reference circuit. So PTAT means proportional to absolute temperature, by the way. So this is the circuit that is very commonly used, or variations of this circuit are very commonly used. This was actually developed in 1974. So let's call this transistor Q1, and I'm going to put the number 1 here, and we'll talk about what this means in a little bit. This will be transistor Q2. This guy will have N. Then we have M3, M4, M5, M6, and now I'll put my 7th and final transistor over here. Where the current leaving this node, this will be transistor M7, is what we'll call our reference current. By the way, down here is ground. And the reference current generated by this guy is given by 1 over R times our thermal voltage, so KBT over Q, times the natural log of N. So we can see here that this circuit, which is supposed to be effectively invariant with supply voltage and temperature, actually does have some temperature dependency. So as the temperature increases, obviously the KBT over Q term is going to go up, but the resistance is also going to go up, and they are roughly at the same rate, so it remains reasonably stable. Typically speaking, you would see variations in your reference current of about 5 microamps for every degree C change. So it's relatively stable, much more so than just using resistors outright, but not super stable. This is a simple version of it. There's I saw a paper from MIT about a much more enhanced version of this that would take probably 3 pages for me to draw, that managed to achieve less than half a microamp of stability over a 100 degree C change in temperature. So they can get incredibly stable if you're willing to add subsequent stages and all of this kind of good stuff to take that into account. Now, this provides a relatively stable biasing current. However, the footprint, and by that I mean the physical space that it occupies on a chip, is actually too large for it to be useful. And let me rephrase that. You don't want to have to do this a whole bunch of times on every single chip for every circuit that needs a current source to bias them. And that's where current mirrors come in. So a current mirror is simply just a circuit that takes this as its input and then makes a copy of it so that you can apply this current elsewhere. And you can use current mirrors to make multiple copies. And you can also wind up scaling that reference current and all that kind of good stuff. Because let's say that you design this circuit for 10 microamps, but it turns out that you need something that's driving 20 microamps to give you a better gain. Well, you just make your current mirror scaling. So that's what we're going to be talking about for the next couple of class meetings. Okay. So in general, our current mirror circuit is going to do something like this. Okay. So we have our reference current, which is generated by one of these band graph reference circuits or something like that, so that we have some stable amount of current. And then we are going to apply that current at the input of our current mirror. And then the output of our current mirror should be a copy of the reference current. And so now we're going to focus on what actually goes into this black box current mirror. So we're going to start by looking at a BJT current mirror. Okay. So in our current mirroring circuit, we effectively have one leg that senses the value of IREF. So that's what's going on over here. This part of it, whatever it happens to be, is sensing what IREF is. And then we have this part over here that's responsible for making a copy. So let's talk about how we're going to make a copy. Okay. How do we generate a current using a BJT? Just generate a current, period. So if I apply some base emitter voltage to a BJT, I'm going to get some collector current flowing through that BJT, correct? So effectively, I'm just going to use a BJT set up like a current source where I have effectively a DC voltage applied across my base emitter terminals, and that's going to cause some DC current to flow through my collector. Okay. So our starting off point is effectively this. Here's VCC. Here's our reference current. I'm going to put a box around this thing. Where this box is our current mirror. Here's our copy current, and then we're going to use, in this case, an NPN BJT as our current source. And then we're still not sure what the sense mechanism is going to look like, so I'm just going to put a black box inside my black box, and we'll sort that out in a moment. Okay. So this collector current IC1 for this transistor Q1 is very obviously going to be the exact same thing as my copy current because of Kirchhoff's current law. And this base emitter voltage, VBE, needs to be whatever that voltage requires to make that collector current happen, okay? So effectively, our output stage for this thing is nothing more than a voltage-controlled current source, which is exactly what a transistor does. Okay. We apply some input voltage, we generate some output current. That is what transistors do. Okay. So now let's talk about the black box with the question mark. Okay. So we need something that takes an input current in and provides us a very specific output voltage. So let's do a little bit of math here to sort that out. Okay. So I can see that I copy will be exactly equal to my collector current. And my collector current is IS1 times the exponential of this voltage VBE1 over VT. And I'm trying to make this be IREF. Let me put a subscript 1 down here that I missed earlier. Okay. So that's what we're trying to have happen. And so now I'm going to effectively just work backwards from this to figure out how I'm going to generate that VBE1. Right? So that voltage VBE1 will have to be generated satisfying this requirement. Our thermal voltage times the natural log of our reference current divided by IS1. This is the voltage that needs to be generated by that black box on the left. What does this equation look like it corresponds to? Just a BJT. Because it's literally just a rearrangement of the BJT equation above it. It's just another BJT, right? Where this sense BJT is effectively just a current controlled voltage source. So we effectively feed our reference current into a current controlled voltage source, which feeds its output voltage into a voltage controlled current source, which in turn gives us our copy current on the outside, right? So we would just replace this black box with a BJT here, which I'm going to call QREF. let's call this voltage VBE ref, and hopefully we can very easily see that the reference voltage for our, or so the base emitter voltage for our reference transistor must be literally identical to the base emitter voltage for our transistor Q1 because the bases are tied together and the emitters are both at ground. It's impossible for those voltages to be different, which means arguably their collector currents should be the same if those transistors are identical, right? So we need Q1 and Qref to be what we're going to call matched transistors. And that matching simply means that IS ref must be equal to IS1, beta ref must be equal to beta 1, etc. Now, we have a little bit of a problem here. Let me draw in IC ref really quickly. Can anybody tell me what the problem is? We have two NPN BJTs here, right? So what direction should the base currents flow? So we should have a current flowing in here. Let's call this IB1. And we should have a current flowing in here. Let's call this IB ref. Does anybody see why that might be a problem? Flowing in opposite directions. Right, so effectively, if IB1 is pulling this way, that's taking away from the collector current and all of that kind of good stuff. So how are we going to fix that? Diode connection. So effectively, if we tie this node to the base, then now our reference current supplies those base currents. Now that has a consequence. It's going to introduce a small amount of error, meaning that our copy current will no longer be exactly the same as our reference current, because our reference current is going to be that copy current plus the base currents, okay? So let's look at what that error mathematically comes out to be. Okay. So let's say that IC ref is equal to IS times EXP of VBE over VT times 1 plus VCE1 over VA. I am intentionally left off, that should be VCE ref over VA. So I've intentionally left off the remaining subscripts on the VBE, the IS, and the VA because we're assuming that we're dealing with matched transistors where all of those things are going to be the exact same thing. However, there is nothing that's forcing the collector emitter voltages on both sides of this thing to be equal, so we're going to take that into account just in case. Okay. Just as a quick aside thing here, IB ref is just going to be 1 over beta times IC ref. Over on the copy side of our current mirror, we should have the relationship IC1 is equal to IS times EXP of VBE over VT times 1 plus VCE1 over VA. And the base current for transistor Q1 is just 1 over beta times IC1. So now what I'm going to do is I'm going to apply Kirchhoff's current law at this node. And I'm going to apply Kirchhoff's current law at this node and put those results together and see how close my copy current is to my reference current. Okay. So applying KCL at the node that I've circled in pink, we would have I reference is equal to IC ref plus IB ref plus IB1. Everybody okay with that? Now we're going to substitute things in. So that's going to look like IS times the exponential of VBE over VT times 1 plus VCE ref over VA plus IS over beta exponential of VBE over VT 1 plus VCE ref over VA. And then this is still the same addition here. IS over beta EXP of VBE over VT times 1 plus VCE1 over VA. And I can observe that literally every single one of these terms has a common factor of IS times EXP VBE over VT. So I can just take that part out. And now I need to figure out the other stuff, right? So I have a factor of 1 plus VCE ref over VA plus 1 over beta times 1 plus VCE ref over VA. So I can lump those guys together, giving me a factor of 1 plus 1 over beta times 1 plus VCE ref over VA. And then I also have a factor of 1 over beta times 1 plus VCE1 over VA. And this is about as far as I can simplify this piece. Okay. So now we're going to apply Kirchhoff's current law at the node that I circled in light blue, which is literally just saying that I copy is equal to IC1. Okay. So I copy is IC1 is equal to IS times EXP of VBE over VT times 1 plus VCE1 over VA. And I can rearrange that to find that IS times EXP of VBE over VT is equal to I copy divided by 1 plus VCE1 over VA. And I can now substitute that into my original equation, right? So that substitution is going to look like this. So we'll have I ref is equal to I copy divided by 1 plus VCE1 over VA. And then that thing is multiplied by 1 plus 1 over beta times 1 plus VCE ref over VA plus 1 over beta times 1 plus VCE1 over VA. And finally, rearranging, we find that our copy current, I copy, is I ref times the following ratio. So in my numerator, I'm going to have the 1 plus VCE1 over VA. And in my denominator, I'm going to have that big expression, 1 plus 1 over beta times 1 plus VCE ref over VA plus 1 over beta times 1 plus VCE1 over VA. Now, just for simplicity's sake, let's say that the early effect was neglected. Okay. With the early effect neglected, that means that all of our VAs are infinity. Which means this term right here is just going to go to 1 because we're going to have 1 plus 0. This term right here is going to go to 1. This term right here is going to go to 1. And so this is going to come out looking like I ref times 1 over 1 plus 2 over beta. So this ratio is going to be pretty close to 1, meaning that our copy current is going to be pretty close to the reference current, but it's not quite going to be there because, as I mentioned, those base currents are leaching away some of the reference current. Well, let me ask you guys a conceptual question, which you may not be able to answer, but it'll be okay. What do you think would happen if we tried to make additional copies of that reference current? This term is going to keep getting larger and larger and larger, right? So if we had another identical transistor, let's call it Q2, this would look like 1 plus 3 over beta. If we added another one, it would be 1 plus 4 over beta, et cetera, et cetera. So every single one of the identical base currents that our reference current needs to supply introduces more and more and more error into our ability to copy. Okay? In a couple of minutes, we're going to talk about a way to mitigate that. Spoiler alert, the answer is yet another transistor. But before we do that, let's talk about how this current mirror kind of works and different ways that it can be applied. So, keep these notes organized. All right. So we can make multiple copies. simply by just adding other transistors, in, right? So if we start with our baseline current mirror, like so, right? Here we've made one copy. So let's call this I copy 1, where this is transistor Q1. Well, I could just put another transistor over here. And as long as I tie the base of this transistor to the base of my other transistors, I should have a roughly identical copy I copy 2. And I can keep on doing that for n number of copies, but like I said, that's just going to introduce subsequently more and more and more error. Now, being able to make multiple roughly identical copies of a single current definitely does have its uses, but it would be great if we could make different currents with this one stable thing as well. Okay? So if we want to scale our reference current, we can do that by just putting those transistors fully in parallel. So let's say that we're trying to scale I copy. So we might have a situation like this. So this is going to look pretty similar here for a moment. But now we're going to tie all of these collectors together. Also, like so. And here is I copy. So let's say that this is transistor Q1, Q2, and Q3. What do we expect, or excuse me, all the way up to Q sub n? This will erase. There we go. So what do we think is going to happen here? So this can easily be explained just by using Kirchhoff's current law. That's going to be our bread and butter for today, right? So all of these transistors, Q ref, Q1, Q2, Q sub n, they all have literally the exact same base emitter voltage. So because they all have the exact same base emitter voltage, they should effectively have the exact same collector current, right? Well, we know the collector current for Q ref is going to be pretty close to I ref. So that means each one of these is going to be carrying a current of pretty close to I ref. And we just add them all together because all of those collectors are tied together at the same node. So this should be close to N times I ref. Okay. Now, I'm not going to draw it like this probably ever again. Okay. Instead, I'm going to do something like we saw right here. I just put N telling us the number that we have in parallel. So typically speaking, we might represent like 3 transistors in parallel as something like 3 AE, okay? We typically represent it by 3 or whatever number AE because effectively what we're doing is we're scaling up the area of the emitter whenever we're putting those things in parallel like that is realistically how the device is functioning as if it behaves. So 3 transistors in parallel is the exact same thing as a single transistor that has triple the emitter area. So that's how we represent that. So this is how we can get a current that's larger than our reference current. What if we need a current that's smaller than our reference current? We put transistors in parallel on the reference side because that means that our reference current is going to be split up among those, which is going to yield a lower base emitter voltage, which will give us a smaller copy current, right? So we might have something like this. Hold on, my computer is about to die because something isn't plugged in, and that something is unplugged at some point. All right, sorry about that. So here's IREF. And in this case, we might have something like this. So we could call this QREF1, QREF2, all the way out to QREF-M. Let me make my penmanship slightly less shitty here for a moment. So M is going to be the index of how we scale the reference side so that it's not obviously the exact same thing. All these are going to be tied together. And then on this side, we would just have our normal copy transistor where we have some current, I copy. And I already explained it a moment ago, but just in case you weren't checking, obviously this IREF is going to divide evenly among these identical transistors, which is in turn going to yield a smaller base emitter voltage that's common to all of these transistors. And because that base emitter voltage is smaller, I copy is going to be less than IREF, and it's going to be less than IREF by a factor of 1/n. Now, yes,
In this case, still get inside.
there are already diodes connected. Oh, sorry, you're correct. Yeah, sorry. You are absolutely correct. Thank you, James. I missed this little loop right there. Thank you for that. 100% right. We still need our reference current to be supplying all of our base currents, or it's going to go very poorly very quickly. You're absolutely correct. Okay, so hopefully it shouldn't be any stretch of the imagination to say that we could actually do both of these things at the same time to effectively be able to provide any integer over integer multiple of our reference current that we could ever possibly need. So if we scale, so if we had something like this, just for the sake of argument, actually, let's work an example. Okay. With numbers too. Crazy, right? No, this is bananas. I haven't used numbers in weeks. So let's say that we have our reference current IREF, don't care what it is. We're not at the numbers part yet. Here's our transistor QREF, and we have a scaling factor of 2 on this side. Here's our transistor Q1. We have a scaling factor of 3 on this guy. So this will be I copy 1. And let's also give ourselves transistor over here, which we'll call Q2, that has a scaling factor of 5. Tie our bases together, like so. So let's say that beta is equal to 100, and I'm trying to find the error that's introduced in my copy minutes. So let's label some things here really quickly. This is going to be IC ref, IC1, and IC2. Here we have IB ref, IB1, and IB2 like so. What do we think the relationship between IC1 and IC ref is going to be? So 3/2, absolutely right. What about IC2? 2.5 times, 5/2, absolutely right. Nothing remotely difficult about this part. So now let's apply Kirchhoff's current law at, let's call it this node right here. We're going to neglect channel length modulation so that we don't have several different VCEs to deal with, because that's just going to piss out everybody off. Okay. So if we apply KCL at that node, we should see that we get IREF is equal to, so I have an IC ref. Okay. I also have an IB ref, which is just IC ref over beta. Yes. No? Yeah. So only the reference transistor is diode connected. Yes. All the others are not, because we need to allow VCE to float effectively. So we're going to have IC ref over beta. So that's our IB ref term. Then we're going to have IB1, which is just going to be IC1 over beta. And we've already expressed IC1 in terms of IC ref. So that's going to look like 3 IC ref over 2 beta. And then we have IB2, which is just going to look like 5 IC ref over 2 beta. Hopefully, pretty obviously, we can simply factor out IC ref from this thing. So that's going to look like, sorry, that should not be an equal sign there. So 1, I'm going to express as 2 beta over 2 beta, so that I'm putting everything in terms of a common denominator. My next term of 1 over beta is going to look like 2 over 2 beta. My next term contributes a factor of 3 over 2 beta. And my last term contributes a factor of 5 over 2 beta. So this is simply IC ref times two beta, and then 2 plus 3 plus 5 seems like 10 to me. Over 2 beta. So now let's look at our copy current I1, right? So I copy 1 is exactly the same thing as IC1, which is just 3/2 IC ref. Well, if we rearrange this relationship right here, right? Let's do it over here so I can explain exactly what I mean. So IC ref should just be I ref times 2 beta over 2 beta plus 10, right? So that's going to give me 3/2 times I ref times 2 beta over 2 beta plus 10. This part right here is the error. So if we were dealing, let's just really quickly so that we can see that the error is going to be the same regardless of which copy current that we're looking at. If we dealt with I copy 2, that's just IC2, which is 5/2 IC ref, making the exact same substitution. We have I ref times a factor of 2 beta over 2 beta plus 10. So as long as we take all of the different copies into account at the beginning, they're all going to experience the exact same amount of relative error. Okay. So our error is going to be simply 1 minus 2 beta over 2 beta plus 10, which comes out to be 4.762% for a beta of 100. So this means that our copy currents are 4.762% lower than 3/2 of I reference and 5/2 of I reference, respectively. All right, class ends in 4 minutes, so I do not have enough time to fix this error by introducing a source follower into this guy. So that's what we're going to kick things off with on Monday. All right, thank you guys. Yes, sir. Oh, for sure. That's what we're going to talk about once we finish the PJT. So typically, these include that's how my transition is so far as making carry more. The reason why I got that transition from using MOSFET for everything is all about availability and cost, and that's nothing to do with performance. The VJC performance better in every fundamental way. The MOSFET transition is only they're more expensive, so we only. Yes, that's just bring up the middle over here. Yes. So let me scroll.
wondering how you get from the.
So that is just a shorthand notation for these three directly connected. So all bi-parallel is a three-terminal device, so that means all of their bases are at the same node, all of their collectors are at the same node, all of their emitters are at the same node. Right, because they're.
Yeah.
Right. So this is making one version of with the rest.
Yeah, I did.
So realistically here, 10 total.
It does not take 15 minutes
I
more
would
than
have
that.
two in parallel, here, two in parallel, here, five in parallel.
I know, I can do that.
Give them, copy that are related to that.
That's what you think, and I'm trying to take a peanut butter on it.
Yes. Yeah, but all of them got back, all of them in parallel. Yeah, a lot. I'm not- All right, what else?
I asked you about the output too. So for the game, so I took my this is for the M2 and this is my RDA
Mhm.
and then so my B initial like right here, this one versus this one, and my B out is gonna be this one.
Out is just gonna be the drop over this guy.
Yes, drop to it. Yeah, this bit is current, so it's gonna be. Oh my God. That's so nice.
Maybe, I don't know.
Yeah.
So,
To make sure that I'm correct. I'm correct, like the current here, drop over this one, for the out, right?
so, so I'm looking at this right here. So you have Vn is equal to VGS1 plus the voltage drop over this guy. Okay, so I agree with that. What I don't agree with is that the voltage drop over this guy is just GM VGS1 times R3 in parallel with R01 for a couple of reasons. A, R3 isn't in parallel with R01 because that's not ground.
Yeah.
Also, you're not taking into account that so the current flowing down through this guy is gonna be GM1, VGS1, but it's also going to be V out over R not one, so V out minus the voltage at this node divided by R naught. Yeah.
So this one gonna be equal, this one plus this one, drop to this one.
Yep, so yes,
Like this one, VR minus VGS right here, drop to this one, right?
Yeah. you might want to call this voltage like, so I think we did this in class, so I'm not even expecting you to have to do this part.
E or something.
Yeah, so,
Let's go
exactly,
like E right here and then.
yeah, so it
Yeah.
should be extremely similar to what we did in class. So that's the error that I'm seeing, and so if that's not correct, then the other stuff should be correct.
Yeah, and the V out.
Okay, on my way there, it wasn't.
It's just like.
And I was like,
drop
maybe
to
I'm
that.
lucky enough.
So if you're gonna do this, you're gonna wind up doing KCL at this node here and KCL at this node here, and then
Okay.
using that system to solve for kind of everything.
Okay.
It's gonna be gross.
Silly question.
Yes.
So I know it's copying the current, but like, wouldn't we want that I copy to go the other way, like, for copying the current to like power the different things? Like, see the current, and do I just not understand?
So right now, we are effectively developing things that would bias PNP amplifiers, because the current source is on the bottom. We would need current mirror that. So. No, this is pretty easy, right? So. Right now, we're developing. So let's just call this guy right here I copy, and that represents the copy current that's generated by our NPN current mirror. So this would be VCC.
Okay. So you can use the P, okay.
Yeah. what we're gonna see in a little bit is we can change this to give us a current on the top side by connecting our NPN current mirror to a PNP current mirror. And then that will move the current source above.
You can't just draw a funny wire like this.
No. And guess what? Adding the extra current mirror, of course, introduces more error.
All right, thank you.
Yep.